Hi, welcome to lecture 21 of multivariable calculus. This is a big one because today we talk about Green's theorem. Green's theorem is the second of our four big theorems in vector calculus. The first was the fundamental theorem of line integrals that we saw last time. Today, Green's theorem, and then we'll get to two more in the coming weeks. We have important thing to know about Green's theorem is to know the statement first of all. What does it say? Or, at least write it down then, and then know the ingredients for that statement, right? What does it relate to? And by doing that, we get a better handle on what it really says here. And then more advanced analysis, we'll talk about things like scalar curl and divergence in 2D. Now, we're not going to get to those in this video here, but we will get to them in a later time. Here. Okay, so we've been talking about line integrals of vector fields, and again, that's where Green's theorem is going to come in. But generally, what does a line integral of vector field f over a curve C measure, right? It's the flow of f along C, right, in general, right? That's the number you get out of this. How much does the vector field f kind of flow along the curve C here? But Green's theorem applies when C is of a particular kind, namely it's the boundary of some region in the plane, and I'll call that D here. So we say C, and we use this little partial symbol here in the context of sets to talk about boundaries. That can be pretty confusing if you're thinking about partial derivatives, and I understand why you'd be confused. But here, C is a curve, right? It's the boundary of the solid of the region in the plane D. So D would be this, right, kind of solid region inside. C is the curve that forms the boundary, right? The thicker blue, darker blue path here, right? So there's a powerful theorem when we have what we call a simple closed curve. That's what makes C the boundary of a region. Closed because it comes back to itself, right? Simple because it never crosses itself at each point. And when you have a simple closed curve, what you have is the boundary of some region in the plane, and that's when Green's theorem applies. So contrast that quickly with fundamental theorem of line integrals. That applied to conservative vector fields, but to any curve. Green's theorem will apply to any vector field, but only to simple closed curves. All right. So let's get to the statement of it. Here it is in its glory. All right. Now, before you get your eyes crossed at all the symbols and letters here, right? We'll take it apart one piece at a time, see what each piece is, and then it should make a little more sense that these things fit together. So on the left, right, we have a line integral, right? And the little circle here says that we were doing a line integral along a closed curve, right? So that's the little symbol means, it tells the reader, we're doing it around a closed curve. The little partial D here says we're going around a closed the boundary of a region D, right there. So the left-hand side is a line integral. The right-hand side we haven't seen in a little while, but that's a plain old double integral in the plane. So I've got a region in the plane. I'm going to find the double integral of a scalar vector field with respect to area there, right? So D is a simply connected region. Simply connected here just means it doesn't have any holes in it, right? Just a plane surface, and we can deal with the simply connected bit at another time. Boundary of D right here is a counterclockwise simple closed curve forming the boundary of D, right? As we've indicated, right? So if you're the boundary of a region in a plane, the boundary has to be closed, and right, perfectly because it's simply connected, it's a simple curve here. And lastly, F, right? Think of that as a vector field with components P and Q. So if you look on the left-hand side of this expression here, that is the line integral of the vector field F over the boundary of D here. So if we have all those pieces here, we realize we do already know what everything in this statement is. On the left, we have a line integral around the boundary, right, for a general vector field with components P and Q. Here, it's counterclockwise oriented there. And we see that that's equal to some double integral over the interior. Right, so D is the interior here. We relate a integral on the outside to a double integral over the interior. And this guy's a scalar here, right? I've got a partial derivative of Q. Q is a scalar. partial derivative is a scalar. P is a scalar, its partial derivative is a scalar, right? Difference is a scalar. So this quantity in here is just some scalar that we're adding up over the whole region. Right? This is a plain old double integral like you've done for several weeks now. All right. Now, what makes Green's theorem remarkable is that it's exactly this relation that equality holds. The number we get from integrating the flow around the outside is the same as the number we get from integrating this quantity on the inside. Now, that's not intuitively obvious if this is the first time you're looking at it. Like, what in the world is this quantity? We're going to get to that a little bit more, talk about what number this thing is, what it measures here. But what I do want you to appreciate right away is that this theorem is actually of a kind with all the big theorems we've seen in calculus, which is to say it relates a measurement on the boundary of something to the total change on the inside. So the fundamental theorem of calculus did that, right? You integrate a derivative over an interval, and it tells you that you can evaluate that by just looking at the change of the function at the endpoints, right? F of b minus f of a is equal to the integral of f prime of x dx over the range a to b. So a measurement on the inside, right, the integral relates to a measurement on the boundary, right? Change there. Fundamental theorem of line integral was kind of a generalization of that, where we had an integral of a conservative vector field, so it's like a derivative over a curve, and it turned out it was just a change in potential at the endpoints. Right? So again, it related the inside of the object to a measurement on the boundary. Green's theorem also has that property, but now we're moving up to a higher dimension. Right? We've got a region D in the plane here. Right? Here's a picture. Right? Again, the kind of solid blue region is D here, and some measurement over the whole interior of it, namely the integral of this quantity, dq dx minus dp dy, is equal to an integral of the vector field around the outside. Right? That's what Green's theorem says. Right? And when we look at the next big theorems of this course, right, which will be Stokes' theorem and the theorem of Gauss, they also have this property that we have a measurement on the inside of something, right, relating to a quantity at the boundary of them. Okay, I'd be doing a disservice to you if I didn't offer you something at least resembling a proof, some kind of justification for this theorem. So that's what we'll do next.
So how do we know this theorem is true? Well, first of all, we're going to boil it down to a rather simpler case. And we should see that the theorem is equivalent to both of these equalities holding, really kind of like the P side and the Q side, if you will. Right? These are equivalent to the statement of Green's theorem. And it should be easy enough to see that it's equivalent, because if both of these were true, we could add them together on both sides, and we get the statement of Green's theorem, right? Which again is that the integral around the outside of a region integrated against a vector field PQ is equal to the double integral over the interior of that region of this weird integrand qx minus py over the inside. And I say this system is equivalent because if we knew Green's theorem to begin with, we could just set q equal to 0 and we get this statement, or set p equal to 0 and get this statement. Conversely, right, if we knew both of these were true on the left, we could add them together and we'd get back to the statement of Green's theorem. So they are equivalent, and for that reason, we'll just concentrate on one of them, right, and prove this statement. The other side is analogous with a little bit of work can be worked out. Okay, but it turns out we're not going to prove it in complete generality. We're going to look at a specific kind of region, namely a region in the plane that can be written as the area bounded between two functions of x here. So not every region can be written this way, right, as having a boundary on the top and the bottom that are graphs of functions of x. However, it's true that every region that Green's theorem applies to can be chopped up into these guys. So this isn't a complete proof of every case, but it is sufficient to give you the flavor, right, of what's going on. So we're going to prove the top theorem. So here's a general drawing of such a region, right? We have our bounds on the left and right of A on the left and B on the right. And then I've got the bounds of the functions g of x on the bottom. So we see y equals g of x here, and y equals f of x on top. All right. And so we want to prove something about the line integral around this region, right, which I'll call the boundary of d of p dx, right? So that's the line integral we want to do here. Now, that curve comes in 4 components, right? So I'll name each of them in turn. I've got C1 here, C2 on the right, C3 on top, and C4 on the left. So this guy can be written as the sum of those 4 line integrals, right? The nice thing about integrals, we can add up we can compute each piece and then add them together. Now, immediately, even before I write them off, I hope you see that 2 of those integrals are going to be 0, right? Without knowing anything about p here, C2 and C4 are vertical pieces of our curve, right? And so, in other words, x is constant along here. It's not changing. So, integrating with respect to x along this curve is going to be 0 automatically, regardless of the values of p. And same on this side. So really we only have 2 pieces to go. So I've got the integral of c1 p dx plus the integral c3 p dx. Just the top and the bottom are the only ones that contribute to this computation. Okay, so now we're just going to go compute these guys, but we're going to be a little bit more clever about this. We're going to parameterize both pieces, but parameterizing C1 is going to be pretty easy. It's a graph of a function going left to right. We know exactly how to do that. C3, however, goes backwards, and so we're going to use the trick that to evaluate the integral of C3, we'll subtract the integral going backwards. And so the way I write that is as follows. So this is going to be the negative, right? So I'll pull that negative sign out here for the whole expression. The integral of C3, or along minus C3 p dx minus the integral along C1 p dx. Now, there's a reason I chose that way of writing the signs. We'll see that why in a second. So now all that's left to do is to parameterize C1 and what I call minus C3, which is just C3 traversed from left to right. So that becomes pretty easy. All right, so I'll take R of t for C1, and I'm not going to do anything fancy. It's the graph of a function, so I'm just going to use the parameterization t, g of t. And t is going from a to b. So t is playing the role of x, of course, here. And I'll do the same trick for what I'll call minus c3. And going left to right there, looks almost the same. R of t equals t f of t. There. And again, t goes from a to b. We have our parameterization, so the next step is fairly straightforward. We're going to convert these line integrals that we see here into integrals in t there. So what I've got so far is now I've still got the integral of the whole thing, p dx, right, is going to be minus the integral from a to b, right, and we'll do c3 first, so that's going to be p of x and y, but remember x and y here are t f of t. There. And I'm going to bring in the other, sorry, not q, but the other term, which was p t g of t. And since they're both being integrated from a to b, I set it up just right. I can pull this into one integral. Right? If we see back over here, right, I've got the difference between these integrals here, but I parameterize them carefully so they have the same t-values, so I can pull them in to one integral here. Okay, so that looks fairly straightforward. Now is where the magic happens. The next step is the most important of this whole business and takes a little bit of thought to understand what happens, but it's really what unlocks Green's theorem and see that it's true. We're going to turn this, what is a single integral, into an iterated integral, which is going to represent a double integral. So rather than evaluating this integral here, I'm going to concentrate on this integrand here. And I'm going to ask you to think about this object for a second. So it's a difference between two functions, right? It's a function p of two variables. But more specifically, the difference between these two functions for any given t changes only in the second variable, right? So you see that the first argument of t is the same, right? So fixed t, right? These two are the same. What's different is in the second variable. So the clever bit is to recognize this. This is the total change in p for a fixed x value for a change in y. And so the next step is an application of the fundamental theorem of calculus. You should have expected it would come up in this computation here. And so the difference, right, of a function at two endpoints, is the integral of the derivative. But what that function is the function p, where the x-coordinate is fixed and the y-coordinate is changing. So this becomes the integral from g of t on the bottom to f of t on top, right, of the derivative of p with a fixed x component. That's what the partial derivative of p is with respect to y. Right? That's a deep idea, so I'm going to let you can rewind and hear me say it a few times here. But the total change of p, right, with a fixed x value with a total change in y is the integral of the derivative in y. Right? So that's where the y pops out here. And then I need another dummy variable, right? I'll call it s there to give the total change, ds, right? Because now the fundamental theorem tells me that this integral of this derivative with respect to s is the same thing as p, the difference of p at g of t and f of t. So you can pause the video and look at this line for a few minutes to convince yourself that you understand how I got from one statement to the other. All right? Okay, and now that you've unpaused, right, and appreciate this grandeur, look at what we have here. This is exactly an iterated integral, right, over the interior of this region, right? So the variables are called t and s here, but right, remember, integration variables don't matter. Right? So t is playing the role of x, goes from a to b. S is playing the role of y. It goes from g of t up to f of t here. And so that can be written in general double integral form as minus the double integral over the interior d of the y derivative of p with respect to area there. And so actually we've done it. The integral of p dx, right, around the border over here is equal to minus the double integral of the partial derivative of p with respect to y, right, on the inside, right, of the area. This is the partial derivative of p with respect to y there. Right? And so that first statement holds for these regions. And I'll leave it up to you to fill in the details to really complete Green's theorem at your leisure, if you like. It is not required. The next statement, which you can still see at the top up here, involving q's, you kind of have to flip your perspective and work this way if you want the theorem to work out just right here. But you can trust that it holds, and so all of Green's theorem is the same. So there you have it, right? it is the proof, or this little argument is not one you have to memorize, but it's worth going through slowly to see that you understand it, seeing kind of where the argument turns over using the fundamental theorem. We go from a single integral here to a double integral. That's what allows us to say it's there. And hopefully it reinforces what these objects are, which is really what we're after, is appreciating what a line integral around a curve is versus a double integral over the interior. And that in this special case, they get related, right, exactly in this way. Okay, come to class, we will do examples, and lots of implications of Green's theorem. Green's theorem is deep and powerful, and just something I like quite a bit. I feel like it feels like you're doing magic, actually, at some point, where you get something for, it seems like you shouldn't be able to get. You can learn about the interior of a space just from the boundary. And that is a profound idea. But we'll continue that next time. Thanks.